December 7, 1941. Pearl Harbor burns. America enters World War II. Within 6 weeks, the United States military faces a crisis more devastating than any naval defeat. A crisis that threatens to paralyze every tank, truck, aircraft, and landing craft in the American arsenal. Japan has captured 97% of the world's natural rubber supply. Without rubber, the American war machine cannot move, cannot fly, cannot fight. Military planners estimate 18 months until complete operational collapse. The countdown has begun. What nobody knows is that the solution already exists, locked away in a laboratory notebook belonging to a chemist whose colleagues mocked his experiments as worthless, whose methods were dismissed as stupid, whose materials were considered industrial garbage. Dr. Waldo Semon had spent years heating and mixing a brittle, useless plastic that every other chemist had abandoned as hopeless. His supervisors told him to stop wasting time. His peers laughed at his persistence. But in 1926, Semon had accidentally created something that seemed impossible. A flexible rubber-like material made from polyvinyl chloride, the most worthless substance in industrial chemistry. 15 years later, that stupid trick would save the Allied war effort. This is the story of how one chemist's refusal to accept failure, combined with American industrial capacity operating at levels that seemed superhuman, transformed a laughingstock experiment into the synthetic rubber program that kept millions of soldiers moving, fighting, and winning. It's a story about chemistry, desperation, and the moment when mocked innovation became the difference between victory and defeat. The situation in Washington after Pearl Harbor was unlike anything the nation had faced before. In the weeks following the attack, every cabinet meeting seemed to begin with the same question: how much rubber do we have left? Reports flooded in from every branch of the military, and every one of them carried the same dreadful news. The numbers didn't add up. The Navy's reserves were dwindling. The Army's supplies were being rationed. The Air Corps had barely enough to maintain its training program, let alone a global campaign. General Brehon Somerville, the hard-driving head of Army logistics, put it bluntly: without rubber, gentlemen, the trucks stop. And when the trucks stop, the war stops. There were suggestions, some wild, others desperate. Could rubber be recycled? Could it be stretched thinner? Could old tires be melted down? Scientists from the National Bureau of Standards quickly tested the ideas. The results were grim. Recycled rubber lost strength, cracked in cold weather, and turned brittle after a few months. It was a stopgap, not a solution. By early 1942, the government instituted the most severe rationing system in U.S. history. Gasoline wasn't being rationed for lack of fuel, but to keep tires from wearing out. Every mile driven by civilians meant one less mile for an Army truck. New car production was halted. Rubber toys, garden hoses, even raincoats vanished from store shelves. The American public began to realize just how deeply their lives were tied to a single, suddenly unavailable material. The media, meanwhile, fanned the panic. Headlines screamed, "Rubber famine feared." Army warns, "Supplies may run out by summer." Radio commentators painted apocalyptic pictures of tanks stranded in deserts, airplanes grounded for lack of tires, convoys immobilized. Behind closed doors, President Roosevelt listened quietly as his advisors debated solutions. Finally, he raised a hand. "Gentlemen," he said, "the Japanese have taken our plantations, but they have not taken our brains." And with that, he authorized what would become the largest scientific mobilization in human history: the creation of a synthetic rubber industry from the ground up. The task was entrusted to a single man, William Jeffers, the tough, no-nonsense former president of the Union Pacific Railroad. Roosevelt made him the new rubber czar, a wartime position with sweeping powers. Jeffers could commandeer factories, reassign workers, seize patents, and order the construction of new plants, all without waiting for Congress. Under Jeffers, the Rubber Reserve Company was born. It was more than an agency. It was a national emergency project, one that would unite corporations, scientists, and engineers under a single mission: to create a new kind of rubber. But there was just one problem. Nobody knew how to do it on the scale required. That challenge would fall to a quiet chemist in Akron, whose accidental invention was about to change the course of the war. Long before the war, in the peaceful 1920s, Dr. Waldo Semon had been one of hundreds of industrial chemists working in obscurity. He wasn't a soldier or a politician, just a man fascinated by materials. Born in 1898 in Demopolis, Alabama, Semon had grown up during an age of invention. Edison's light bulb, Ford's automobile, Bell's telephone, all had transformed daily life. By the time Semon earned his PhD in chemistry, the industrial world was hungry for new materials. The B.F. Goodrich Company hired him to research synthetic coatings for metal, materials that could prevent corrosion and wear. But Semon's curiosity wandered. In his free time, he experimented with plastics, strange new substances that were just beginning to emerge. Among them was polyvinyl chloride, or PVC. PVC had been discovered in Germany decades earlier, but every attempt to use it had failed. When heated, it turned black and brittle. When cooled, it cracked. It was regarded as useless. Most chemists simply gave up. But Semon didn't. There was something about it, he later recalled. It had the right elements: carbon, hydrogen, chlorine. But it needed a friend. Something to make it come alive. That friend would be the plasticizer, a small molecule that could slip between PVC's long polymer chains and make them flexible. For years, Semon tested every substance he could find: castor oil, linseed oil, camphor, even animal fat. The results were always the same: disappointment. Then, in 1926, by chance, one of his mixtures changed. Instead of burning or hardening, the material cooled into a soft, flexible sheet. It bent without breaking. It stretched without snapping. It was waterproof, heat-resistant, and durable. Semon stared at it in disbelief. He'd done what the scientific world thought impossible. He'd turned brittle PVC into a flexible, usable material. When he showed his bosses at Goodrich, they were skeptical. "Looks like rubber," one said, "but why would anyone need fake rubber?" The truth was, in 1926, nobody did. Natural rubber was cheap, abundant, and reliable. Semon's discovery went largely ignored. But Semon wasn't discouraged. He refined his process, testing new plasticizers and applications. Flexible PVC found niche uses in wire coatings and gaskets, but it remained a footnote in industrial chemistry. Until, 15 years later, the world ran out of rubber. Then, suddenly, Semon's forgotten formula became priceless. When the Rubber Reserve Company was formed in 1942, it brought together an unlikely coalition of rivals. Goodrich, Goodyear, Firestone, Standard Oil, and U.S. Rubber, corporations that had spent decades battling for market dominance. Now, under government order, they had to work together. They called the program the Synthetic Rubber Project, and it would become the greatest collaborative research effort in history, second only to the Manhattan Project. Semon's flexible PVC would play a key role, but the broader mission was even bigger: to produce not just substitutes, but true synthetic rubber on a massive scale. The government allocated $700 million, equivalent to more than $12 billion today, to build new chemical plants. Every major university and laboratory in the country joined the effort. Chemists experimented with polymers like Buna S, Buna N, and neoprene, each with unique properties. At the center of it all, Semon's lab in Akron became a hive of activity. Day and night, the lights never went out. They experimented with PVC blends, searching for materials that could replace rubber in thousands of non-tire applications. Wire coatings, seals, hoses, boots, rainwear, and aircraft insulation. Each experiment was a battle, against time, against chemistry, and against exhaustion. Semon's notebooks from this period read like the diary of a man racing fate. Entries are terse, urgent, often smeared with fingerprints. Mix failed, temperature control off. Batch 71, improved flexibility at 120 degrees Celsius. Possible substitute for insulation lining, test tomorrow. His wife later recalled that he rarely slept. He would come home at 2 in the morning, she said, and go right back by 6. Across the country, the same feverish rhythm pulsed through laboratories. The air smelled of solvents and rubber smoke. Every experiment brought new hope and new hazards. At the DuPont plant in New Jersey, an explosion destroyed an entire lab wing. At Firestone's pilot facility in Ohio, workers developed chemical burns from experimental compounds. But they kept going, because the stakes were clear: success or defeat. By summer 1942, pilot plants began producing flexible PVC at industrial scale. Inspectors from the War Production Board tested the results. The material withstood heat, pressure, and gasoline exposure. It could replace rubber in nearly half the applications the Army required. It wasn't perfect, but it worked. For the first time since the fall of Singapore, the United States had a path forward. By 1943, America's factories were running 24 hours a day, 7 days a week. Steel mills thundered. Chemical plants hissed and steamed through the night. From the outside, it looked like chaos. But inside that chaos, a miracle was forming. The synthetic rubber program had moved from theory to reality, but the scale of the challenge still bordered on madness. The country needed 600,000 tons of rubber a year to meet military demand alone. And by spring 1943, it was still producing barely a fraction of that. The solution lay in 3 key compounds: butadiene, styrene, and sodium catalyzers. When combined under the right conditions, they created Buna S, a rubber-like polymer tough enough for tires, hoses, and tank treads. Butadiene came from petroleum, a product of cracking gasoline and refining alcohol. Styrene came from ethylbenzene, another chemical derived from benzene and ethylene. None of these materials had ever been produced in the necessary quantities. Factories had to be designed, built, and operating before engineers even knew if the processes would work. It was, as one historian later wrote, like assembling an airplane while already in flight. The War Production Board pushed forward anyway. Standard Oil designed the first butadiene plants. US Rubber handled polymerization. Goodyear focused on curing and testing, and all of it was coordinated by the newly formed Rubber Reserve Company under William Jeffers' no-nonsense leadership. When engineers told him a project would take 2 years, Jeffers slammed his fist on the table. "You've got 8 months," he said. "If you need more time, sleep faster." The government poured money into construction. Workers flooded into boomtowns like Baton Rouge, Baytown, and Akron. Entire new neighborhoods appeared overnight: barracks, canteens, schools, and recreation halls for the men and women who would live beside the machines that powered the war. Newspaper reporters called it the Great Industrial Gamble. The gamble wasn't just whether the factories would work, it was whether America could build them before the war was lost. The stakes were simple. If production didn't rise fast enough, the invasion of Europe could stall before it even began. And yet, through the chaos, something extraordinary was happening. Ordinary Americans, machinists, welders, chemists, pipe fitters, were doing what the experts said couldn't be done. By the end of 1943, the United States was producing more synthetic rubber in a single month than it had in all of 1941. What began as panic had become progress. While the factories roared at home, the consequences of the rubber shortage played out on the battlefield. In North Africa, supply convoys stretched for miles across barren sand. The sun scorched the vehicles, and the rubber tires baked until they cracked. Mechanics worked around the clock patching leaks and swapping wheels. In the Pacific, humidity and salt water attacked every gasket, every hose, every seal. Planes sat idle for want of spare parts. At Guadalcanal, Marines boiled their boots to soften the soles when they turned stiff in the tropic heat. Every footstep was a reminder. Without rubber, even the simplest task became agony. And yet, the tide was turning. By late 1943, synthetic materials began to trickle into the supply chain. Flexible PVC insulation protected the electric systems in new aircraft. Buna S tires appeared on army trucks. Vinyl-coated ponchos kept soldiers dry in the rain-soaked jungles. The transformation was quiet but profound. Each crate that left an American port now carried the fingerprints of scientists and factory workers who had never seen the front lines but whose labor made victory possible. A pilot flying over Italy in 1944 might never have known that the fuel hoses on his bomber came from a lab in Akron. A nurse on a hospital ship might not realize that the tubing in her hands was the product of a plastic discovered by accident 18 years earlier. But history would remember. By the time Allied forces landed on the beaches of Normandy in June 1944, every vehicle, aircraft, and ship in the invasion fleet contained synthetic rubber somewhere in its design. Rubber had once been a natural gift of the tropics. Now it was a human creation, born from chemistry, necessity, and stubbornness. Back home, engineers faced new battles, not against enemies, but against physics itself. Scaling up chemical production was a nightmare. At laboratory scale, a chemist could heat a few ounces of butadiene and styrene with perfect precision. At industrial scale, reactions took place in 200,000-gallon tanks. Heat distribution, pressure fluctuations, and contamination could destroy entire batches worth thousands of dollars. Every problem required a new invention. When rubber sludge fouled the pipelines, engineers invented new filtration systems. When polymerization stalled, they built better temperature regulators. When catalysts ran out, metallurgists developed substitutes using domestic ores. Many solutions came from improvisation. At one plant, an engineer suggested using repurposed dairy mixers from a local milk company to blend chemicals. It worked. At another, workers used steam engines from decommissioned trains to power polymer pumps. The war had turned the entire nation into a laboratory. The government even launched emergency training programs to produce more chemical engineers. Short, 12-week crash courses that taught physics, chemistry, and plant safety. High school graduates were transformed into technicians almost overnight. Semon's team at Goodrich trained hundreds of new workers in the art of vinyl production. Each batch had to be mixed precisely. Too hot and it burned. Too cold and it stayed brittle. He called his method learning by burning. By mid-1944, the rubber industry was producing more than 100,000 tons of synthetic rubber every month. A few years earlier, that number would have seemed absurd. Now it was routine. America had done the impossible. The success of the synthetic rubber program did more than keep vehicles rolling. It changed how America thought about materials forever. The war became, in many ways, a war of substitutes. Natural silk was replaced by nylon. Aluminum took the place of steel, and rubber, that irreplaceable tropical treasure, had been reborn in laboratories. Scientists joked that chemistry had replaced geography. But the victory came with lessons written in sweat and danger. Synthetic rubber wasn't perfect. It aged faster, cracked under extreme heat, and sometimes carried hidden weaknesses that didn't show until months later. Engineers had to learn how to work with it, to cure it, to design around its flaws. Still, it was good enough to win. By 1945, over 80% of all rubber used by the Allied forces was synthetic. From tank treads to life rafts, from gas masks to bomb fuses, synthetic materials had become the unsung heroes of the war. In a letter to the War Production Board, one general wrote, "You have given us something greater than supply. You have given us motion." The Rubber Reserve Company had proven something extraordinary, that science and industry, when united under urgency, could perform miracles. The same spirit would soon carry America into the atomic age. In the summer of 1945, as the war in Europe ended, Dr. Waldo Semon finally left the factory floor. He was older, tired, but still restless. His invention had helped save the Allied war effort, yet he remained the same quiet, curious man who once mixed chemicals in a forgotten corner of a lab. He never sought fame. He didn't appear in parades or pose for photographs. When reporters asked how it felt to have created a material used in every corner of the war, he simply said, "It was useful. That's all I ever wanted something to be." But history would remember him differently. By war's end, flexible PVC had become one of the most versatile materials on Earth. It was used in medical tubing, electrical cables, raincoats, flooring, and even phonograph records. What had begun as a stupid experiment had become an empire of modern materials. Semon continued to work at Goodrich for nearly 2 more decades, earning over 115 patents across plastics and coatings. He retired quietly in 1963, leaving behind a legacy that stretched far beyond chemistry. When he died in 1999 at the age of 100, obituaries celebrated him as the man who made plastic bend. Perhaps his greatest achievement was proving that persistence can outlast mockery, and that sometimes the most revolutionary ideas begin as mistakes. Because sometimes history is moved not by grand strategy or political will, but by a single act of stubborn faith in an idea. And that is the story of the man who bent plastic, and with it bent the course of history itself. The guns fell silent in 1945, but the machinery of war kept humming. Across America, the plants that had once turned out tanks and munitions now found themselves with new orders. Peace had come, but the machines refused to rest. Factories that produced synthetic rubber for military convoys pivoted overnight to civilian production. The materials born from desperation were now being molded into the comforts of modern life. Flexible PVC, Semon's creation, found itself in a world eager for convenience. Wire insulation became household wiring. Ponchos became raincoats. Medical tubing found new life in hospitals that were treating civilians instead of soldiers. In the years immediately after the war, vinyl seeped into every corner of daily existence. It lined car interiors, wrapped electrical cables, coated furniture, and filled radio casings. Its versatility seemed limitless, its affordability miraculous. The chemical plants that had been built under government contracts became private assets, their equipment redirected to serve booming post-war industries. DuPont, Firestone, Goodrich, and Standard Oil all rebranded their wartime successes as peacetime miracles. Adverts proclaimed a new era. Science serves the home. Television commercials showed smiling housewives with vinyl aprons and children playing with rubber balls made from synthetic polymers. The same chemistry that had once kept tanks rolling now made living rooms brighter and kitchens cleaner. But beneath the optimism, there was a quiet unease. The war had proven that the United States could create anything. But nobody yet understood the consequences of creating everything. For the engineers who had lived through the synthetic rubber crisis, the speed of this transformation was breathtaking. In 3 years, they had learned to build an industry from scratch. In 5, that industry had remade the modern world. Factories no longer followed the rhythms of nature, of harvests, seasons, and supplies. They followed chemistry. Rubber no longer came from trees, it came from barrels of oil. The war had changed the world's definition of natural, and there was no going back. The story of synthetic rubber was not just the story of one man or one invention. It was a collective triumph, built by tens of thousands of unknown hands. In Akron, the self-proclaimed rubber capital of the world, parades celebrated the workers who had powered the industry. Men and women marched under banners that read, "We kept the wheels turning." But when the crowds went home, most of them returned to ordinary lives. The chemists who had stayed awake for days during wartime experiments went back to quiet laboratories. The factory workers returned to civilian production, molding vinyl flooring and household goods instead of military gear. Still, the transformation they had helped spark was irreversible. In 1939, America had imported virtually all its rubber from Asia. By 1945, it was producing nearly 1 million tons of synthetic material every year, and exporting the know-how worldwide. Germany, defeated and divided, had pioneered synthetic rubber early in the war with its Buna series, but America's systematized production eclipsed it entirely. Britain and Canada followed suit, building their own post-war plants with American assistance. Synthetic rubber became one of the foundations of the modern global economy. It was in every tire, every airplane seal, every electrical cord, every shoe sole. And yet, for many of those who had worked in the program, the memories remained bittersweet. They remembered the pressure, the sleepless nights, the chemical fumes, the explosions that punctuated the rush to innovate. Some lost friends to laboratory accidents or toxic exposure. When asked later if it had been worth it, one chemist replied quietly, "We didn't think about worth. We thought about survival." That sentiment echoed the moral weight of an entire generation, a people who had faced extinction and built salvation from science. And at the center of it all stood Waldo Semon, whose once laughed-at experiments had become the backbone of a new industrial civilization. By the 1950s, vinyl had conquered the American imagination. It was sleek, shiny, and modern, the material of the future. Architects used it to build waterproof floors and flexible window frames. Designers used it for furniture, colors bright and bold like never before. And in recording studios, vinyl revolutionized sound. The vinyl record, light, durable, and capable of holding an entire symphony, became the heartbeat of post-war culture. Millions of Americans danced, dreamed, and fell in love to the sound of grooves pressed into Siemens' flexible plastic. Meanwhile, chemists continued refining the formula. They developed new additives that made PVC even stronger, more resistant to sunlight, more transparent. The substance once dismissed as industrial waste now defined the look and feel of modern life. In schools, children used vinyl-covered notebooks. Hospitals stocked vinyl gloves and IV tubing. Cars rolled off assembly lines with vinyl upholstery that gleamed in the sun. By 1960, global PVC production had surpassed 1 million tons per year. Yet the success carried an unintended irony. The same material that had symbolized progress and freedom during the war was slowly binding humanity to a new dependence, not on rubber trees, but on oil. Every inch of vinyl came from petrochemicals. Every ton required energy from refineries and power plants. In freeing itself from natural limits, humanity had tied itself to another kind of chain, one built from fossil fuel. But few in that era could see it. The world was too busy celebrating its synthetic prosperity. To them, vinyl was the triumph of human ingenuity, the proof that chemistry could solve any problem. And for a time, that illusion held. Decades passed, and the synthetic age began to show its cracks. By the 1970s, scientists started noticing strange new problems. Rivers near chemical plants turned cloudy and lifeless. Workers handling vinyl chloride, the gas that formed the basis of PVC, developed rare forms of cancer. Suddenly, the miracle material of the 1940s looked more complicated. The very traits that made PVC so durable, its resistance to heat, water, and decay, made it nearly impossible to destroy. Discarded vinyl products piled up in landfills and oceans. When burned, they released toxic fumes. When buried, they persisted for centuries. The public's faith in chemistry began to waver. Environmental movements emerged, demanding accountability from the industries that had grown rich on wartime inventions. Synthetic rubber, plastics, and vinyl were no longer seen as miracles, but as double-edged swords. Yet amid this reckoning, Siemens' story stood apart. He had never claimed his invention was perfect. He often warned that materials were only as good as their purpose. In a 1970 interview, he said quietly, "We make things to serve us. The question is whether we can serve wisely." Those words would prove prophetic. Because as the century turned, the world faced a new crisis, not of scarcity, but of excess. Too much plastic, too much waste, too much of the very thing that once saved civilization. And yet, even as critics decried the synthetic age, few could deny its achievements. The same vinyl and rubber compounds that polluted rivers also powered hospitals, insulated homes, and protected millions of lives every day. The legacy of 1942, the desperate, frantic year when the world nearly ran out of rubber, had become permanent. Humanity could no longer imagine life without the substances it had created in crisis. Waldo Semon never sought wealth or fame, though he earned both in quiet measure. He received more than 100 patents and several of chemistry's highest honors. Yet when asked about his career, he always deflected praise. He believed that invention was less about brilliance than persistence, the willingness to keep trying after everyone else gave up. When he finally retired from Goodrich in 1963, he left behind laboratories still running on his principles: curiosity, precision, and patience. In the decades that followed, as the world debated the ethics of synthetic materials, Semon remained philosophical. "Every discovery," he once said, "is a reflection of its time. Ours was a time of war. We made what we had to make." He lived long enough to see his creation change medicine, construction, and music, and long enough to hear people question its cost. When he died in 1999 at the age of 100, obituaries celebrated him as one of the most influential industrial chemists of the 20th century. But perhaps the truest tribute came not from scientists, but from soldiers. At reunions and memorials, veterans of World War II sometimes spoke of the equipment that carried them through the storm. The hoses that didn't leak, the boots that didn't crack, the wires that didn't short in the rain. All of them, unknowingly, owed a debt to a chemist who refused to stop stirring beakers of useless plastic. In the end, Semon's story is not just about chemistry. It's about vision, the kind that sees possibility in failure and persistence in ridicule. Because sometimes history is moved not by grand strategy or political will, but by a single act of stubborn faith in an idea. And that's the story of the man who bent plastic, and with it bent the course of history itself. Even decades after his death, Semon's influence continues to ripple through science and industry. Every vinyl floor in homes around the world, every insulated wire transmitting electricity, every medical tube delivering life-saving fluids owes a debt to his stubborn experimentation. Modern chemistry classrooms still teach plasticization, the process he accidentally discovered, as a foundational principle of polymer science. In laboratories, students repeat the very experiments he once performed, marveling at the same strange flexibility that baffled his peers. The broader synthetic rubber program also left an indelible mark on industrial engineering. Plants built in the 1940s evolved into sprawling complexes, producing not only rubber, but an array of chemicals essential to modern life. Engineers refined processes developed under wartime urgency into standard practices for scaling laboratory chemistry to industrial production. The lessons of collaboration, speed, and ingenuity have since informed countless technological projects, from semiconductors to pharmaceuticals. And yet, the story of synthetic rubber is also a story of responsibility. The environmental and health challenges posed by PVC and other synthetic materials serve as a constant reminder that human ingenuity must be paired with care and foresight. Modern chemists, engineers, and policymakers grapple daily with the balance between innovation and sustainability, a balance that Semon himself had intuited. Materials are only as good as the purpose they serve. Ultimately, Waldo Semon's life exemplifies the quiet power of persistence, the uncelebrated heroism of curiosity, and the transformative potential of what the world initially dismisses as worthless. His work turned desperation into opportunity, scarcity into invention, and a laboratory curiosity into a cornerstone of modern civilization. In the end, millions of lives were changed, not by a general's orders or a politician's decree, but by a man who refused to accept the limits of rigid plastic, and whose stupid trick became a legacy that endures to this day. The legacy of Waldo Semon extends far beyond the laboratory benches of Akron or the frantic wartime factories that hummed day and night. His work was not simply the creation of a flexible material, it was the beginning of a paradigm shift in how humanity could approach materials themselves. Before Semon, industrial chemistry had been largely reactive. Scientists observed natural materials and attempted to mimic or improve upon them. Rubber was sourced from trees, plastics were experimental novelties, and most chemists operated under the assumption that certain materials were inherently limited by their natural properties. Semon's accidental discovery challenged that notion. By taking a substance deemed useless, experimenting with it patiently, and refusing to accept conventional wisdom, he demonstrated that materials could be engineered to suit human needs. Flexible PVC was more than a substitute for natural rubber. It was a revelation that humans could create entirely new classes of materials with properties tailored to specific applications. This idea underpins much of modern materials science, from the development of synthetic fibers to advanced polymers used in aerospace, electronics, and biotechnology. Every time engineers and chemists manipulate molecular chains to create a substance that did not exist in nature, they are following a path first illuminated by Semon's persistence in a dusty laboratory. The impact of Semon's work also underscores the symbiotic relationship between innovation and crisis. History often remembers the battles, the political decisions, and the generals. But the synthetic rubber program reminds us that wars are also won in laboratories and factories. The urgency of 1942 created conditions under which ideas that had previously seemed irrelevant or impractical became invaluable. Flexible PVC, once ignored as a laboratory curiosity, was suddenly recognized as critical to the survival of millions of soldiers, sailors, and airmen. This transformation, from obscurity to strategic necessity, illustrates a broader truth about human innovation. Necessity not only inspires invention, it accelerates it. Under pressure, humans can solve problems that were previously deemed impossible. Semon's work, and the massive industrial mobilization it enabled, is a case study in the power of coordinated, high-stakes problem-solving. Engineers, chemists, and factory workers collaborated in unprecedented ways, compressing years of industrial development into a matter of months. This phenomenon, repeated throughout history whenever society faces existential crises, shows how human ingenuity is often unlocked, not through comfort or leisure, but through urgency and necessity. The scale of the synthetic rubber program also reshaped American industrial capacity permanently. Prior to World War II, chemical production in the United States was robust but limited, oriented largely around existing demand for consumer goods and basic industrial materials. The government's investment and coordination during the war created a network of factories, pipelines, and logistics systems capable of producing materials at volumes and complexities previously unimaginable. Flexible PVC, Buna S, neoprene, all required precise control of chemical reactions, meticulous handling of raw materials, and innovative engineering to scale laboratory experiments into industrial processes. The techniques developed to solve these problems became the foundation for post-war American chemical and manufacturing industries. Today's massive polymer plants, chemical refineries, and research laboratories operate on principles refined during that extraordinary period. The synthetic rubber program demonstrated that industrial capacity is not a static resource, but a dynamic one. It can be expanded, redirected, and optimized to meet extraordinary demands when necessity dictates. The lessons learned from that mobilization continue to influence industrial planning, emergency preparedness, and large-scale project management even decades later. Moreover, Semon's work illustrates the importance of vision and persistence in science, particularly in fields where the immediate utility of a discovery may not be obvious. For 15 years, Semon's colleagues dismissed his experiments as pointless. Flexible PVC was considered neither plastic nor rubber, and its potential applications were unclear. But Semon persisted, driven not by fame or reward, but by a belief in the unexplored possibilities of his material. That single-minded dedication to exploration is a hallmark of many of history's great scientific achievements. Often, breakthroughs occur not in fields that are immediately profitable or recognized as important, but in areas where curiosity, patience, and resilience intersect. Semon's story is a reminder that innovation frequently emerges from the margins, from experiments that appear trivial or absurd at first glance. Without his willingness to continue tinkering with worthless substances, the United States might have faced catastrophic shortages that could have altered the course of World War II. His example endures as an encouragement to scientists, engineers, and creators. Sometimes the most transformative discoveries come from ideas the world has already written off as impossible. Finally, the human element of Semon's achievement cannot be overstated. While the story of flexible PVC and the synthetic rubber program is often framed in terms of chemistry and engineering, it is ultimately a story about people, individuals confronting immense challenges with determination, ingenuity, and courage. The factory workers who stayed nights on end, the engineers who improvised solutions on the fly, the chemists who experimented tirelessly with unknown chemicals, all contributed to a collective success that no single person could claim. Semon's role, though central, was part of a larger tapestry of collaboration and perseverance. The story emphasizes that science and technology do not exist in isolation. They are woven into the fabric of society, reliant on teamwork, infrastructure, and human commitment. Every hose, every boot, every electrical wire that carried a soldier safely through war represents not just chemistry, but the culmination of human ingenuity, effort, and resilience. In this light, Semon's stupid trick is emblematic of the broader potential of humanity. To take something dismissed as useless, to experiment relentlessly, and to transform it into a tool that can save lives and shape the future. His legacy is therefore not only the material he created, but the enduring lesson that perseverance, curiosity, and courage, in the face of doubt, can change the world.